Okay, yeah, please roll whenever you're ready.
So this is the second talk I'm giving for the Ricci Flow seminar. So thank you very much for having me again. And on today's talk, I'm going to talk about different topics related to the Hallström system. So as a follow-up to the first session, I want to discuss a notion of harmonic metrics for the Hallström system. And by the half of the talk, we'll change topics and speak about a new set of equations which haven't appeared in the literature, and that will show some nice new interesting features. So let's go with it. I firstly want to recall what was the setting in last week's talk. So I will have a compact complex manifold, which I call Calabi-Yau of possibly non-Keller type, by which I mean just having a holomorphic volume form. This is a section of the canonical bundle, which is nowhere vanishing. And moreover, a pair of holomorphic vector bundles. Okay, so then I say that a Hermitian metric on the manifold and a pair of Hermitian metrics on the bundles are a solution to the Hallström system with this alpha, this string tension, if the following equations are satisfied. So in the first place, I ask for both Hermitian metrics to satisfy the Hermite-Einstein condition. So they are both instantaneous. This is not always the case in the literature, but for me, I will require both to be Hermite-Einstein. The second condition is the Di Latino equation or the conformally balanced equation. And as you can see, this selects a balanced class. Balanced class is a cohomology class in both Chern cohomology that is represented by a metric, by the power of a metric that is positive. And third, in the third place, this is the most mysterious equation. We were talking a bit about it in the last day, which is called the anomaly cancellation equation by physicists and by mathematicians, the Bianchi identity. So the main result I was discussing last day is that if I am given a solution to the Bianchi identity, just the third equation, then I can produce a bundle, a holomorphic bundle, which has the structure of a holomorphic current algebroid of a special type. And if, moreover, this solution is of the whole set of equations of the whole Hallström system, then I can produce a metric which is pseudo-Hermitian. It's Hermitian, but possibly of definite signature that satisfies the Hermite-Einstein equation on the current algebroid. Okay, so this equation, okay, this is all I want to say for now. So this is the main result of last week. So now I will discuss some stability conditions in a sense reminiscent of GIT. I want to discuss what is the suitable notion of stability in algebraic geometry, which is well suited for the Hallström system. So suppose we have a solution for the Hallström system, and in the sense I have said, I can produce a holomorphic current algebroid and a Chern connection of some metric, of some non-positive metric. So yes, this is actually nearly always the case, unless the bundle of this middle term, let me return for a moment. So if you see this Bianchi identity, the bundle B0, which appears in the middle term, if I have this bundle, if this bundle is non-trivial, then we have no slope stability because the metric is not positive. So we cannot apply immediately the Donaldson-Uhlenbeck-Yau theorem, which would tell me that since I have a metric that satisfies Hermite-Einstein, then my bundle is slope stable. But here I do not have that because the metric will not be positive. So one thing one can say is, okay, if the source of non-positivity is this bundle, then you can consider just to remove it, okay, and consider the same system, but without this V0 bundle. So this solution is not satisfactory, and this is why. So if we assume this, we remove this bundle and just take a solution consisting of Hermitian metric and the Hermitian metric on the remaining bundle, that is a solution to Hall-Strominger, then it happens that the metric must be Kähler and the Hermitian metric on the bundle must be flat. So if we precisely are looking for good non-Kähler geometry, then we surely must not assure this. This was already known in the seminal papers by Candelas, Horowitz, Strominger, and Witten when they were studying, well, when they were deriving what is now called the Hall-Strominger system from a physicist point of view, from compactifications of a heterotic string theory to 4 dimensions. This is the physical origin of this system. But here now, this was already known, but now we can recast it in the following approach. So from a GIT point of view, we are going to derive this result. So as I was saying, if we remove this middle bundle and consider a solution to the remaining whole Hall-Strominger system, then in fact, my metric, my natural metric, is Hermite-Einstein and is positive, just because I removed the part which accounted for the negativity. So now we can indeed apply the Donaldson-Uhlenbeck-Yau theorem, and we would have that the bundle is polystable. But because it is polystable and I have and always the cotangent bundle of a current algebroid is a subsheaf, polystability tells me that since they both have, this is a very easy result, they both have 0 slope, then polystability says that this bundle be holomorphically and metrically split, where the metric splitting is given precisely by the Hermite-Einstein metric. And so now one only has to check, has to write what is the Dolbeault operator on this bundle and see which off-diagonal terms have to vanish for this Dolbeault operator to be split, to be holomorphically split. And one reaches the conclusion that a torsion term for the metric has to vanish, and so the metric must be Kähler, and the curvature of the Hermitian metric on the bundle must be vanishing, so the metric must be flat. Okay, so it is the same result as we already knew, but now from a GIT point of view. And this is the new the novelty, the new approach we are going to take in the following. So okay, it seems that if we want some non-Kähler solutions to the Hall-Strominger system, we have no choice but to admit that the metric must be indefinite. But okay, one could say, okay, but just restrict to manifolds which are Kähler, because I recall that the main aim of this was to see the feasibility of what was called a rates fantasy, which was a proposal for connecting different components of the moduli space of Calabi-Yau threefolds across their boundaries through some complex surgeries that were called conifold transitions. At the Hall-Strominger system should serve as a way of geometrizing, of having a control over these transitions. So the best place to test this must be precisely on manifolds which admit a Kähler structure. So now we are going to study the behavioral solutions in the main set, in Calabi-Yau threefolds, which are Kähler, algebraic Calabi-Yau threefolds. So on these manifolds, we have these cones in the sense of positive algebraic geometry, which are called the Kähler cone and the balance cone. The Kähler cone is very well known in the literature. It is the set of classes that are represented by a Kähler class. And there is also this balanced cone, which is classes in 2-2 cohomology. All of the complex cohomologies in Kähler manifolds are the same. And these are the classes that are represented by the square of a matrix. So the square must be closed 2-2 form. It must also be a metric. So there is this paper by Fu and Xiao that studies the relation between these cones in Calabi-Yau manifolds and Kähler manifolds. They present this map which they show it is actually very easy to check that this map is well defined, and that this extends to even to the boundary of these cones. So one takes a class in the closure of the Keller cone and shows that the square is well defined inside the closure of the balance cone. And now, what I said before is that conifold transitions are used to glue different components of the modular of Calabi-Yau threefolds along their boundaries. So conifold transitions should take place in these cohomology classes, on classes that are balanced and that are in the boundary of the Keller cone. Okay? So this is the natural place to study. So first, we take it easy and study what happens in the interior of the Keller cone. And it happens the following thing. So we have now a Calabi-Yau manifold of Keller type and have a solution to the Hallström-Inger system. I have a manifold which is Keller, but I don't assume my solution to be Keller. Okay? It's just the geometry that is Keller.
Just a question, like,
Yes.
why don't you allow the balance class to be on the boundary as well?
Well, we start by this point, okay, and we have this result. We have yet to study this is first the easier.
All right, okay.
The easier version, okay. So yeah, and now we assume that the balance class is given in is such that is a square of a Keller class. So if you want, it is in the image of this map S when restricted to the Keller cone, to the interior of the Keller cone. Okay, so I have this situation, and I assume that my holomorphic current algebroid associated to a solution of the Hallström-Inger system is polystable with respect to this class. Then it follows that the metric is scalar and H0 and H1, the metrics on the bundles, are flat. So it is not a very promising result, right? I want solutions which are not Keller, but in the end, all I get is scalar. It is scalar data. So what we conclude from here is that slope stability, which is the traditional notion to measure stability in algebraic geometry, together with some other Giesecker, etc. notions, this appears not to be very well suited to study the moduli of solutions to the Hallström-Inger system. So we may want to explore different notions. Okay, this is the main message of these rigidity results or no-go results, if you want. So now we are these results tell us that we have to rethink our approach. So now we will be inspired by the theory of Higgs fields to proceed. And how do we do that? Okay, so we start with a solution to the Hallström-Inger system and consider this holomorphic string algebroid together with its natural Turing connection. Then, okay, it seems that the non-positivity of the metric, we cannot do anything about that. So we just, let's forget about it for a moment and just regard this Turing connection as a complex connection. In the same way that in the theory of Higgs bundles, the connections of interest are flat connections and nothing more, just flat complex connections. And here we have just complex connections, which are represented by this DG. And we already know that the ones of our interest are Hermitian Yang-Mills. So we can do the following. We now fix now a positive Hermitian metric. Now this H, and in the following, the notation H will denote a positive Hermitian metric. Then we can have this decomposition a la Hitchin. My term connection, I will split it into two terms. One, which is Hermitian with respect to this new positive Hermitian metric which I have fixed, and the remaining part, which must be skew Hermitian. Now the question is translated to these heights. So now, what equations should we impose on heights, or what are the Hermitian metrics we want to consider? And the proposal is to derive some equations for heights from a moment map. And this will do the following. So my setting will be this one. I will consider a balanced manifold. Here X will be compact complex, and omega a balanced metric. And my phase space on which the moment map will take place is consisting of holomorphic orthogonal bundles. Q is now some holomorphic orthogonal bundle. I will not require it to be current or anything. Implicitly, I will be thinking of that, but I won't assume it. Just a holomorphic bundle together with an orthogonal pair. Okay. Okay, so this will be my phase space or my parameter space. The space of complex orthogonal connections on this path. And the group that will be acting on it will be the complex gauge group. I won't be saying anything about unitary until later. For the moment, it's just complex, and required to be compatible with the structure. So with the pairing here on my orthogonal. So now it is a similar proceeding as in the Atiyah-Bott case over Riemann surfaces, but here we the differences are that my manifold is not a Riemann surface, is a higher dimensional, and that my connections are complex. So what I have is a complex symplectic structure given by this formula, similar to the case of Atiyah-Bott, with these subtleties. Here, this structure is complex symplectic, okay? So no holomorphic symplectic, no real symplectic, is complex symplectic. And then I repeat here the same formula, and the result is that the action of this complex gauge group is Hamiltonian with respect to the symplectic structure. And the complex moment map is given by the following formula. So the zeros of this complex map, for this complex moment map are precisely the Hermitian Yang-Mills connections. Okay, the ones I am interested in, because that is what the Hallström-Inger system gives me. So now the key point of this study is that once I fix a positive Hermitian metric, this will induce a hyperkähler structure on the space of connections on this holomorphic orthogonal band. How is this? So I will spell this out. Given this data, the ones I was talking about, I have a splitting of everything in this setting in two parts. One which is unitary with respect to the Hermitian metric, and one which is skew unitary. Okay, this happens for this space of one forms, and this happens with the rest of the structure. The phase space is going to be restricted to the part of unitary connections and some other part which is skew Hermitian. Okay, and we have also a distinguished subset of the gauge group, those gauge transformations which are unitary. And the complex symplectic structure is separated into a real part and an imaginary part. And these now real symplectic structures can be checked that they are both compatible with different complex structure to a unique Riemannian metric. Here I have the formulas for these two complex structures. So it is very likely that to this point, a hyperkähler structure is going to appear. And this is actually the case. So the result is that we can complete this tuple, this Riemannian metric omega I and omega j, to a hyperkähler structure. We have a third complex structure given by the composition of both of the previous ones, and a new real symplectic structure. And it happens that the action now of the restricted group, the unitary part of the gauge transformations, acts on the space of complex connections, but now it is Hamiltonian for the three of the real symplectic structures. Okay, so this is the content of this
Sorry,
result.
Raul,
Yes.
is it right that still, like, up to this point, the choice of H is arbitrary? Is it
Yes, but yeah, but now I'm going to select
Sure.
once.
Okay.
But yeah, but okay.
I
To
just
be
make sure I
honest,
understand, that's all.
yes, yeah. So it is arbitrary, but it has to satisfy some compatibility condition with the pairing. Okay, just that. And this compatibility
Okay.
just means the same that happens in Cn. So in Cn, you have an obvious bilinear pairing of complex vectors given by component-wise multiplication. And the Hermitian metric is just composing this pairing with an anti-holomorphic involution in one of the terms. Okay, so it is the same for this Hermitian matrix. It's just composing my natural pairing I have on this holomorphic bundle, with an anti-holomorphic involution. Just that.
Okay. Yeah. Thank you.
Okay. And so now we are going to do what you want. We are going to select the good H. And how is that? Okay. So first, I have the moment maps associated to the three Hamiltonian actions I have. So here I have these formulas. Recall that what I had at the start is I have it here. I have a complex symplectic structure that amounts to the omega I and omega j, the real and imaginary parts. So I have two Hamiltonian actions, and these both first and second equations amount to the zeros of the initial complex moment map equation, which was that the connection on the holomorphic bundle was Hermitian-Yang-Mills. So here, in this decomposition in Hermitian and skew Hermitian part with respect to H, these are just the equation it results of being Hermitian-Yang-Mills for D. This is the two equations. But now, since I have completed it to a hyperkähler structure, I have a third equation coming here. So now I have a good notion to define. I will define that a Hermitian metric is harmonic precisely if my connection D I started with is a zero of this moment map with respect to the splitting given precisely by H. Is this clear? Is there any question?
Actually, yes, sorry, I think I'm confused. You say it's a function of D?
So D is the connection I started with. D is a connection that is given to me by a solution of the Hallström-Inger system.
D is like DG.
Let me do a very brief recap. So I have a solution to the Hallström-Inger system. Yeah. I have a connection. So now for any Hermitian metric, I can do this decomposition in Hermitian and skew Hermitian parts with respect to some Hermitian connection I have fixed. And now I have this moment map, these three moment maps, if you want, that are depending on the Hermitian metric H. And now I say that H is harmonic. This is my notion of harmonic metric, precisely if this is a zero of the three moment maps. For the first and second ones, this is automatic. I already know, since I have started with a connection that was Hermitian-Yang-Mills. This I know because of the general theory we developed last week about the Hallström-Inger system, that my metric, my connection is Hermitian-Yang-Mills. But so the third one,
sorry, just so I understand, like basically by the definition, or you choose an arbitrary H, which then determines a psi, and then these quantities on the right-hand side of mu I and mu j are secretly just in terms of the original Hermitian-Yang-Mills connection.
Yes, these are actually this one is the skew Hermitian part, and the second one is the Hermitian part.
Yeah. Okay. Yeah, I understand.
or maybe the other way around. I have to think about it. But yeah, they both amount together. They amount for the connection to the Hermitian means, and the new one is the third one. So if a connection, if a metric is such that this splitting produces a zero of this third moment map, I say that this metric is harmonic. Is that okay?
Yes, thank you.
Okay. So, okay, we have a notion of harmonicity, and this in turn is going to give me a notion that is worth studying, of stability. And my notion of stability is going to be the following. So let's say I have a bundle in the conditions as before. I have a holomorphic bundle which is orthogonal, and I have a connection that is Hermitian-Yang-Mills. This is what I will be thinking of because these are supposed to come from a solution of the Hallström-Menger system. So I assume that my connection is Hermitian-Yang-Mills, and also that the 0-1 part of this connection is given by the Dolbeau operator. This is a holomorphic vector bundle, so I will assume the 0-1 part to be the Dolbeau operator of my bundle. This is what the Chern connection of the Hallström-Menger system gives me. So I say that such a bundle is semi-stable with respect to some balance class if it happens the following. For any subsheet of the bundle that is coherent and that satisfies some compatibility with the pairing, isotropy is the most natural one, and such that is de-preserved by this connection I am given, then the slope of f is less or equal than the slope of my bundle, which is 0. That's because of how my bundle is, the slope will be 0. So if for any of such coherent subsheets, the slope lower or equal to 0, and I say it is semi-stable. And the stability and polystability are defined in the obvious way from this semi-stability. So stability will be that the slope is actually lower strictly than 0 for any coherent, for any proper coherent subsheet. And polystability will be, well, the usual thing that if such a inequality occurs, then my bundle will be actually split. Okay? So this will be my notion of semi-stability.
Sorry, how does the moment map act on F? I'm confused.
On F, you mean the curvature?
No, the subsheaf F. Or maybe I'm confused. The meaning of mu sub omega n minus 1 F.
No. So this sorry, yeah,
that's just the usual degree. It's nothing to do with
yes. This mu is the symbol for the slope. Yeah, I didn't say it. This is a parallelism with the usual notion of semi-stability. Okay, so there you have a slope and you have a degree, etc. Here it is much the same thing, but with these new issues that the subsheaf is isotropic and that is preserved by the connection. Okay. So
where are you using the harmonic metric, or is this definition independent of?
Yes, it is independent, but it will appear in a second. But for now, yes, it is independent. And now, what I want to warn you is that this notion of semi-stability is somewhat weird or not usual, in the sense that the setting I'm going to apply it to is to a connection that is a Chern connection associated to some metric data. So usual stability conditions depend on holomorphic or algebraic data. But this is actually going to depend on metric data that for the moment we don't know how to avoid. So this is one of the things that we still don't have clear about this picture. This study is very recent, and there are still some things we don't know how to do properly. Maybe this is the proper way to proceed. We still don't quite understand it fully, but this is the notion that is right for us for now. So yes, this condition we are going to apply to a connection that depends on metric data. And what Arpan was saying is involved in the following result. So this stability notion, we have defined it such that the following happens. So if I have my geometry in which the Hallström-Inger system appears, so a Calabi-Yau manifold possibly of non-Keller type on holomorphic bundles, and a solution to the Hallström-Inger system. And now, additionally, I suppose that the holomorphic current algebroid that it defines carries a harmonic metric. Okay, we don't know if this is always going to be the case, but we assume it for now. If this is the case, then the current algebroid is polystable with respect to the balanced class given by the solution in the sense above. Okay, so usual or traditional slope semastability was very rigid and obliged the solution to be Kähler. But now this is no longer the case if we assume this new definition of stability. It has the issue that we have now to worry about the existence of harmonic metrics in the sense that have been introduced, okay, in this new this current algebra, whether it carries a harmonic metric or not. The thing is that for some examples we have worked out, we do have harmonic metrics. This is what I want to illustrate now. In a family of examples, we have harmonic metrics. So for this, I consider the manifold called in the literature the Iwasawa manifold, that is a homogeneous space of a complex Lie group. So the complex Lie group is the Heisenberg complex three-dimensional group, which is given by upper triangular matrices of this kind, and it is quotiented by a co-compact lattice given by the same sort of objects, but with Gaussian entries in the Gaussian intervals. So this is a compact complex manifold, and much of the exterior algebra computations can be done at the level of linear algebra. For this, we introduce these three forms, which are 1-0 forms, with respect to the natural complex structure that this manifold carries. And the geometry is the following. So we have this manifold that is a compact quotient of a complex Lie group via lattice, and this has a projection to the standard for torus. So complex two-dimensional torus. And here we have a very easy SU3 structure to write down. This given by this omega 0. It is a Hermitian metric that is balanced. This is a result that applies to many manifolds of this kind. The result, proved by Avena and Grassi, tells us that any Hermitian metric which is left invariant with respect to the action of this of the group itself, together with some unimodularity condition, tells us that this metric is balanced. But we don't need to worry about this. We can actually prove that it is balanced by a direct computation. So this is a metric, and this omega 1, 2, 3, whenever I write these subindices, these are understood to be wedge products. Okay, this is a holomorphic volume form. And so, as I said, this metric is balanced, and the norm of this holomorphic volume form with respect to the metric is a constant, just because of invariance. So this selects for me a balanced class, which I call this frac B0. And now this is the geometry on the manifold, and I am going to consider a family of bundles. The line bundles will be pullback from line bundles which fiber over the base of, so you remember X has a projection to the 4 torus. So now I choose the bundle coming from the torus, and I remove this V1 bundle that was appearing in the Hallström-Inger system. So now these bundles that I was speaking of can be very much identified by curvature forms. So you can check that the forms that are written here satisfy all the properties that a curvature has. So by general theory, these are the curvatures of Hermitian metrics on holomorphic line bundles. M and P are here 3 integers that selects the topology of this line bundle. Okay, so the first chain class. So now this is the geometry, and we have the following result. So let us pick a line bundle which has the same first chain class as any of the line bundles I had chosen. So let me return for a moment. Let's fix M, N, and P, okay, and choose one of these line bundles. So with the topology fixed, I assume given a holomorphic line bundle, which is topologically the same as the one that I have fixed. Then the first thing I want to say several things. The first thing is that I have a solution to the Hallström system for these bundles. This is just a quick computation that one must do, but is really easy. It's just linear algebra. So once I have a solution for the Hallström system, my main result of last week said that I have an associated holomorphic current algebroid together with a connection that is Hermitian Yang-Mills. So it satisfies this equation, and where the metric is given by this expression in the identification of the current algebroid with the tangent plus the adjoint of the bundle. And that this metric is not going to be positive. But now the key thing is that if we do this little change, if you compare G and H, they are basically the same thing, but for a flip in the sign of the alpha. Then this H is positive because the negativity was here in the part of the bundle, and it is actually a harmonic Hermitian metric on Q. So this Q was depending on this L prime. For each L prime, I have a different holomorphic bundle, but any of this family carries a harmonic Hermitian metric. It's just a toy model in which Hermitian metrics are shown to exist just by direct computation. And so, as a corollary of the theory I have explained up to now, it follows that the current algebroids that I have defined, since they carry harmonic Hermitian metrics, and are polystable in the sense that I defined earlier, okay? It's just a consequence. Okay, so this is the theory of this part of the talk, and now I wanted to give you some questions that, as I said, this theory is not fully developed. There are issues that we don't fully understand. I want to show you some of them. So the first one, I already said that we don't know if the current algebroids we construct carry a harmonic metric or not. In case they do not always, the notion of stability we have is not properly defined, because we assume that such a metric always existed, and we don't have an existence result up to this point, apart from the examples. The second thing is that the harmonicity is, in the classical sense, related to the minimization of some functional. We yet have to exploit many of the features of harmonicity in this context. This is not yet done for the moment. It is in the to-do list. Also, one other thing is that this stability condition was, as I said, related to metric data of the solution to the Hallström system. So the conjecture or the expectation is that the solution of a Hallström system should be unique if we fix some cohomological data. But up to now, this is only just an expectation. This would solve the dependence on the metric data. But for the moment, we don't know that. We have to relate the stability conditions to holomorphic features of the current algebra, linked to the pairing, maybe of the bracket that I forgot to write here. There should be a Dorfman bracket in the current algebra that is a canonical part of the structure. Also, what we have is still only one part of the Hitchin-Kobayashi correspondence. So the result, let me go back here. So this last result here. So I have a solution to the Hallström-Menger system, and there was a harmonic metric. Then the bundle is polystable. So this is this is the easy direction of the Hitchin-Kobayashi correspondence. But now I want to know if the converse holds or not. So this is this may not be the case, but okay, it is in the sorry, I was getting ahead of myself. This is in the to-do list to see if such a Hitchin-Kobayashi correspondence holds or not. And even in the case it does not hold, at least we might be able to use GIT obstructions apart from the obstructions that I told you about last week, which were these Futaki invariants. And also one other very nice thing to think about is if the following happens. So recall that in the theory of Higgs fields, there are different incarnations of the moduli space of the objects of interest. There is the Betti moduli space, the Dolbeau, and the Hodge moduli space, and each of them is defined in a different way and carries a different structure. But in the end, they are isomorphic in some category, let's say, and we can transport one structure to the other moduli spaces, and these structures are not the same. For example, the complex structures, they are defined in the different incarnations of the moduli space of solutions to the Hitchin equations, let's say. They are not the same, and so they conspire to give more structure when they are combined. Here, it is worth studying if such a phenomenon happens. If, for example, the stability condition I have said produces a moduli space with a structure that is different from the moduli of solutions to the Calabi system. This Calabi system has been introduced by García Fernández, Rubio, and Tipler. It's a generalization of the moduli space of for the Hallström-Menger system, and they might in fact have different structures, and we shall see if they are compatible or not. This is also a direction. So this is all for the first. Yes.
Can I just ask, like, so you say like minimization of a functional, you mean sort of understanding solutions of Hallström-Menger as minimizers of a functional? Or do you mean harmonic metrics?
Yes, that was the thing. So harmonic metric in our new sense, we don't still know if this minimizes some functional as harmonic forms in the sense of classical Hodge theory minimizes a functional. We don't know if there is this parallelism or not.
Okay, and do I understand correctly? So like this, like the way you're using the polystability, you sort of assume you have a solution to Hallström-Menger and then further assume you have a harmonic metric.
Yes.
That determines sort of a notion of polystability and and the fact that it is polystable, I guess. Mm-hmm. Is it right?
Yes.
So, I mean, does it make sense to, so now, I mean, if you really wanted to think in terms of like a variational theory, I mean, you just have some, you know, like choice of metric on this algebroid or whatever. I guess, would you want to sort of associate a harmonic metric like to arbitrary data somehow? Or...
Arbitrary in what sense do you mean?
Well, I mean, looking forward to sort of actually like constructing solutions of Hall-Strominger. So now you just have like some metric on your algebroid or something, you know, like defining some energy on candidate
Yes,
metric.
that's the idea, that this functional should be the energy.
And well, but I guess maybe then that's my question, is that the functional depends on a choice of harmonic metric? Or, oh, not really. I guess the functional you define is totally arbitrary. That's right. Okay.
So the functional
is...
should be such that these critical points define harmonic metrics. That should be the way to put it, right? In my understanding. So this is not yet done, but this is what I would expect.
So is it right then that like zeros of the moment map you define determine sort of both a harmonic metric and a solution to Hall-Strominger? Is that the right way to think of it?
Yes, that was the definition of harmonic metric in the first place.
Yeah.
So
yeah.
you remember there was these 3 moment maps. 2 of them came from the fact that I have a connection which I know is Hermitian-Yang-Mills, just because of the theory of the Hall-Strominger system. And now the third one, it's zeros. I define them to be harmonic metrics.
Okay. Yeah. Okay. Yeah. Thank you.
Okay. So yes, this is the first part of the talk, and now I want to speak of a different topic. I'm going to tell you about some new system of geometric PDEs and see some features that it has. So, okay, let me return to the starting point. The geometry that I had assumed for the Hall-Strominger system was the following: a Calabi-Yau manifold, maybe of non-Keller type, and a principal G-man. So now, yes, the Hall-Strominger system asked for 2 holomorphic vector bundles, but now I am going to just work with a holomorphic principal bundle approach because of simplicity. And now, yes, we have this Bianchi identity, a solution to which gives me a holomorphic current algebra. Okay. I told you that if this solution to the Bianchi identity was a solution to the full Strominger system, then I have a Hermite-Einstein metric. But this is actually not necessary. It is just sufficient, but the right, so the exact conditions that it has to hold is in the following proposition. So I'm going to speak a bit of these equations. I give you some, I have to give you what the notation stands for. So just to tell you that the Hall-Strominger system is stronger than having a Hermite-Einstein metric on the current algebra. Okay, so let me give you all the notation. So these are the 3 equations that are actually equivalent to having a Hermite-Einstein metric. The first one here, SH, stands for the scalar curvature, taken with respect to the Hermitian metric of the solution. Okay, so this is the commutator inside the Lie algebra, and this tells me that the curvature must lie inside this bundle. So 1-1 forms taking values in the center of the Lie algebra and also in the unitary part of the Lie algebra with respect to the Hermitian metric. Yes.
Is SH constant in some sense, or it can be? It's a
Yes,
section
it can vary. Yes,
it can vary.
It is not in general a constant. What we know is that it lies inside the center. So, okay, let me put it this way. So this equation is very sensible to the choice of the Lie algebra. For example, if the Lie algebra is abelian, this equation is automatically satisfied. Okay. On the other extreme, if the Lie algebra is semi-simple, then it says that the scalar curvature is actually 0. So you can expect both behaviors. Okay. Okay, this in the literature is a condition that is actually weaker than Hermite-Einstein, but it receives a name, at least in the case when the principal bundle comes from a vector bundle. This weak Hermite-Einstein, it actually carries many of the properties that Hermitian-Einstein metric do, but we don't have the relationship with algebraic geometry of polystability given by Donaldson, Ruddenberg, and Young. So the second of these equations is what we call Young-Mills with torsion. Just because if you see the terms of this equation, the first one is what we would call Young-Mills in the Kähler setting. And the thing is that in the Kähler setting, the second and third term vanish because here we have the torsion terms of a metric. This theta omega is the Lie form, and GC omega is the torsion of the metric. So this can be seen as a non-Kähler generalization of the Young-Mills equation admitting torsion terms. And this third equation is what we call twisted Bismuth-Ricci flat, because this rho B is the form that is defined on the canonical bundle induced by the curvature or of the Bismuth connection. And we have this twist given by this bundle term. Okay, so these are the conditions which are actually equivalent to solving the Hermite-Einstein equation on the holomorphic current algebra. So we want to study which are the natural conditions under which this holds. Hallströminger is enough, but a weaker version is also actually enough. This is what we introduce now. This is what we call the coupled Hermite-Einstein system, given by this set of equations, which I'm now going to explain. So now I assume X is a compact complex manifold. I don't assume anything more. I don't assume it is Kähler. I don't assume that it has a holomorphic volume form. I don't assume anything, just that. This system is in principle defined for any compact complex manifold. And I am giving also a holomorphic principal boundary. Then I say a couple given by a Hermitian metric on the manifold and a Hermitian metric on the bundle satisfies the coupled Hermite-Einstein system with some data, with some central charge that lives in the center of the Lie algebra if the following happens. The first equation is just a weak Hermite-Einstein condition. It is weak because this metric, it does not define in principle anything. It is not a Kähler metric, it is not a balanced metric, it is not anything. What I can do is rescale it to its metric in its conformal class that is Godot-Shon. Then this defines something which is cohomological. But in that case, this set is no longer a constant. Okay, so this is just weak Hermite-Einstein, not Hermite-Einstein. The second equation is related to the twisted the twisted Bismuth-Ricci flat condition I was speaking before. And the third one is the same Bianchi identity as always. This does not change because we want to have holomorphic current algebras, and the Bianchi identity is the equation that defines it. Okay, so now I remark that this system is in principle solvable only if the two following constraints happen in cohomology. So if you look at the second equation and read it in cohomological terms, then it follows this first cohomological equation I have written here. And if you look at the Bianchi identity, then the second term is a representative of the first point triangling class. And so it has to vanish in Botzian cohomology, just because of this equation. So in principle, in any manifold that's satisfying these two equations, this system is solvable. Okay, so now my aim is to construct some solutions of the coupled Hermite-Einstein. So what are the obvious solutions we have at hand? Well, we have the solutions to the Hallströminger system, which is a stronger system. This is the content of this result. So speaking in simple words, if I have a solution of the Hallströminger system, then for this central charge, let me return a moment, this coupled Hermite-Einstein, asked for some data in the center of the Lie algebra for a central charge. If I assume this is 0, then a solution to the Hallström-Inger system gives me a solution in particular to this system. This is the coupled Hermite-Einstein, in which I have set the central charge going to 0. And this is the thing. So what this just says is that the Hallström-Inger system is stronger than this this new system. And okay, it is stronger, but you have to take into account that this new system does not, well, I already said that. So we don't need any of the conditions that I assumed on my compact complex manifold. I don't assume I have a Calabi-Yau N-form, holomorphic volume form. And I don't assume I have balanced metrics. In principle, any compact complex manifold will do. So now I want to give another method of constructing solutions. And we are going to do this related to a parallel theory that has been already studied by Garcia Fernandez, Jordan, and Stritz in the recent paper about the non-Kähler Calabi-Yau geometry and its relation to the pluriclosed flow. So they define this notion. They say that on any compact complex manifold, a Hermitian metric is Bismuth-Hermite-Einstein by definition, if these two things happen. So if the metric is pluriclosed and the Bismuth-Ricci form is 0. So I remind you that this is the curvature given by the Bismuth connection on the canonical bundle. So now, okay, one thing one can observe is that if I remove the principal bundle for the coupled Hermite-Einstein system, then this notion of Bismuth-Hermite-Einstein metric is a solution. So what this tells me is that the coupled Hermite-Einstein system is kind of a completion of this notion when we take into account a holomorphic principal bundle. Okay, one should think in these terms. And we have this result. This result is a correspondence between solutions to the system and Bismuth-Hermite-Einstein metrics in the sense of this paper. So the result is in the following lines. Suppose you have a holomorphic T2 bundle, and that in the total space of the bundle, in this manifold Y, I have a Bismuth-Hermite-Einstein metric that is invariant with respect to the action of the T2 group. Okay, then I can produce at the base a solution of the coupled Hermite-Einstein system in which the Bianchi identity has positive pairing. Okay, and in which the bundle is the bundles we take into account in the Bianchi identity is a sum of two line bundles which have the same topology than this vibration, than this Y going to X that is a T2 bundle. So this is encoded in a pair of first Chern classes, and this will be the Chern classes of the bundles I have to put on the base. Okay. So this is a method for constructing solutions to coupled Hermite-Einstein, supposing we have some invariant solution of some invariant Bismuth-Hermite-Einstein metric. So what I want to do now is give as an application the converse result of what I have explained. So now I am going to start from a solution of the coupled Hermite-Einstein system and produce a Bismuth-Hermite-Einstein metric. And it is just the converse. So now I start by giving myself a compact complex manifold and a pair of holomorphic line bundles. Then on the total space of, okay, so let me cook up first this PI here. These are the frame bundles of Hermitian reductions of these line bundles. So when I have a solution to the coupled Hermite-Einstein system, then I can use these metrics to reduce the structure group of the line bundle to a circle bundle. When I take the fiber product of these two circle bundles, I get a T2 bundle over X. Then this T2 bundle over X has this data, has a bismuth Hermitian Einstein metric that is invariant under the action of the group. So is the result clear? Any question? Okay. So I want to give an idea of the proof. The proof is a nice piece of Hermitian metric. So the first thing is that on this PI, I have generators of the action, and I define a complex structure on the total space of the vibration. Just the complex structure is going to be determined by the complex structure and the base, and in the vertical space, just by taking one generator to the other. There are both. The next thing is to define the candidate to be the bismuth Hermitian Einstein metric. So we just pull up the metric from the base, and we use the chain connections associated to the Hermitian metrics I suppose I have. And I do an extension procedure to regard these metrics as one connections in the total space of I. And then I have this expression for the metric. One checks that that this is a Hermitian metric, and now the supposition is that this is a solution to the coupled Hermite-Einstein system. So I must use the equations. The Bianchi identity corresponds to upstairs having a pluriclosed metric. The twisted bismuth-Ricci flat corresponds upstairs to just bismuth-Ricci flat, using also the remaining equations. So the conditions on the metrics, on the bundles. Okay. So what these two results, this and the previous one in the slide, just tell me that if I have a T2 bundle over a compact complex manifold, then I have a correspondence of solutions to the coupled Hermite-Einstein system, this new system I have been introducing, bismuth Hermite-Einstein metrics upstairs. And the procedure is just reduction together with elementary Hermitian geometry. Okay. There is this correspondence. And this is sort of why we regard this new system to be legitimate. This is the result that we really wanted to have. So we have now a link to something that was studied before. Okay, so now let me move to the following thing. Here I repeat this notion of metric. And now, okay, I have a procedure of taking these metrics and produce a solution to the coupled Hermite-Einstein system. So what are the known solutions for these metrics? So for the moment, there are not many, and they come in the following flavors. So whenever we have a Keller Calabi-Yau metric, then you can see that if from the equations defining a Keller Calabi-Yau, it follows that it is also a bismuth Hermite-Einstein metric. It is very easy, just because whenever one has a Keller metric, the bismuth connection and the Chern connection and the Levi-Civita connection, all these are the same. These are the Keller examples, and the non-Keller examples are the following. So whenever you have a homogeneous even dimensional real Lie group, there is an interesting story that has been developed. So the solutions to the these metrics can be constructed in the following way. So one has to take a Riemannian metric that is B invariant with respect to left and right translations by elements of this group. And also you have to take a complex structure that is left invariant, and it also must be compatible with the Riemannian metric. then this is shown to be actually bismuth flat. So the full curvature tensor of the bismuth connection it vanishes. This is, as I was saying, some work that has been completed by many people in different stages. So now, a question that has been asked before in this seminar was whether all bismuth Hermitian Einstein metrics were as in the above examples. So whenever we have one that is not Keller, then it must be of homogeneous. And well, my proposal is to use this system, coupled Hermitian Einstein system, together with the reduction procedure I explained, to produce metrics that are not of this kind. Okay? That would be the idea. Yeah, that's use the system together with them. Okay, now I want to explain another feature of this new system. So I write here again the equations defining the system. You can read it them. And I recall that these were actually enough to having a holomorphic current algebroid with a Hermite-Einstein metric. And the signature of the metric depends on the signature on the pairing I have on my Lie algebra. What I have been saying a lot of times is that whenever this solution comes from the stronger Hallström system, then the metric is not positive. It cannot be if the manifold is non-Keller. But the interesting new feature that appears here is that when this is just barely coming from the coupled Hermite-Einstein system, the metric can indeed be positive. And so I want to give an explanation of why this new feature appears when we consider this weaker system. So recall that a holomorphic current algebroid of the type I have been studying comes in this sequence, where this AP stands for the Atiyah-Lie algebroid of the principal bundle P. Now, what happens for the Hallström system is that we assume that the manifold is Calabi-Yau. So we have a holomorphic volume form. That is a trivialization of the canonical bundle that is so this bundle is isomorphic via dissection to the structure bundle of the manifold. And so this what implies is that the first Chern class of the cotangent vanishes not just in the round cohomology, but it does in both Chern cohomology. And so this fact that this happens in both Chern cohomology is actually crucial, because then in the extension of Donaldson-Uhlenbeck-Yau theorem to Hermitian manifold, the pairing one has between the first Chern class and Godot-Shon classes to measure the degree of bundles happens between Apley and both Chern cohomology, not the RAM, because we don't have Keller classes. And so what this says is that if the first Chern class of the cotangent bundle is 0, then its degree must be 0, the same as the degree of Q. But then, by polystability, this bundle must be holomorphically and metrically split, which actually tells us that the metric is Keller. Okay? That was what was happening in the Hallström system. The thing is that now I have a system that does not ask for a holomorphic volume form. So this ingredient I had here disappears and the obstruction disappears. So it might very well be the case that the holomorphic current algebroid is polystable, is slope polystable, because I would have a positive Hermite-Einstein metric. Okay? Just because I have relaxed the conditions that I were assuming on my manifold in the Hallström. Okay, so now one last thing I want to comment on is on the, let's say, family in which the coupled Hermite-Einstein system lives. So I want to tell you who are their brothers we know that his father is the Hallström system, we are going to see some of his, let's say, brothers or cousins. So for this, I want to have a Riemannian characterization of the coupled Hermite-Einstein system, and this is the content of this proposition. So I have my geometry, a compact complex manifold, and a principal bundle, and I assume given a solution to the coupled Hermite-Einstein system with vanishing charge, this set that appeared. And this is just manipulations translating what was written in, let's say, the language of Hermitian geometry now into the language of Riemannian geometry. It is just a matter of Hermitian manipulations. Okay? And you can write here what everything means. So there are many Riemannian things appearing, like, for example, the Ricci curvature. You have this tensor that comes from a 3-form and using the metric to contract some of the indices, etc. Okay. Okay, so this is the case. This is just a reformulation in Riemannian language. And the thing is that now we have a generalized geometry interpretation of what this means. So in the work of García Fernández, these terms accounted for the vanishing of the generalized Ricci tensor for a generalized metric in this current algebroid of special type, of string type. This generalized metric is encoded in this Riemannian data. Okay, so a Riemannian metric, a 3-form, and a connection of the bundle. And also for defining the generalized Ricci, we need a divergence, and that is determined by this phi here that appears in the system. And in the case of the coupled Hermite-Einstein system, it is actually the Lie form of the Hermitian metric. So this is one interpretation of the system. And now another one is that when we do a choice for the one form appearing in this Riemannian reformulation, if we set the one form phi to be exact, then these equations actually match the equations coming in the mathematical physics literature under the name of equations of motion of heterotic supergravity. So in mathematical terms, this phi, which was the Lie 1 form, saying that it is exact, amounts to say that the metric is conformally balanced. Okay, that would be the translation. And so this is what I wanted to tell you. Now I want to pose some questions to you. So now you have some work. If you want to pursue this way. So I gave some methods to produce, let's say, abstract solutions. So a method that had an abstract solution and I produced another abstract one, but I would like to have some explicit formulas to put my hands on. So this is the first thing I would like to do, to construct explicit non-trivial solutions, so solutions that don't come from the Hallström system, which I already know that they produce, or to exploit the obstructions that I have using the slope polystability that can happen for the coupled Hermite-Einstein system, as opposed to the rigidity results we saw at the start of the talk for the Hallström system. We expect this to happen even in complex manifolds with no assumptions on having a holomorphic volume form or even on having balanced metric. So a nice place, an expectation to find results are in these S3 times S3 manifolds that admit a lot of complex structures. And for example, the Calabi-Ekman threefolds are of this kind. Also, another thing one would like to do is that this method of presenting solutions to the coupled Hermite-Einstein system from bismuth Hermite-Einstein metric was using reductions via line bundles. We could try to extend this to the non-abelian case. One other thing one would like to do is to sort of understand these equations as an evolution problem. So maybe we are not able a priori to find a solution, but we can set some flow using this Riemannian reformulation, for example, to actually find convergence to a solution. Something that could be following Street's ideas to the generalized Ricci flow. We could try to find a relation between these, if you want, generalized Ricci flow. And one thing that is totally conjectural from this point is to find a spin interpretation of the coupled Fermi-Einstein system. And why I say this, the only, it is not even evidence, but the thing I am thinking of is that the stronger system, the Hall-Strominger system, has a counterpart in spin geometry, which are called the killing spinor equations. And these equations can actually be used to show that the duality holds for a Hall-Strominger system. So it can be translated to other manifolds with other topologies, something that was done by Garcia Fernandez. So maybe it might very well be the case that this weaker system also has hidden symmetries, which is worth investigating. So this is what I wanted to tell you today. Thank you.
Thank you. Thanks, Raul. Are there more questions? Can I just say or ask? I guess you maybe I missed it, but I mean, I guess you can interpret this sort of more general. I guess you called it like the coupled Bismuth-Hermitian-Einstein system as sort of Bismuth-Ricci flat on the total space of the bundle, just with an indefinite metric, possibly indefinite metric. Is that right?
So it can be indefinite metric, but the one thing I was telling you about is that we can expect that the metric is now positive because of this relaxation issue. So the metric can now be positive, and then it amounts on the total space to a Bismuth-Hermitian-Einstein metric, and now it is a positive metric.
Yeah. But even sort of more generally, formally in some sense, like you still have some metric on the total space of the bundle, which potentially could be indefinite on
sure. Yes
in the bundle directions, and it will still, and this system that you guys describe can be interpreted as like Bismuth-Ricci flat on that total space, right? Yeah, okay. By the way, I just mentioned, as far as constructing examples, you know, Alberto, who's here, you know, they have this whole big construction now of families of where the sort of usual Riemannian type Ricci tensor, Bismuth-Ricci tensor is 0. And of course, this is subtly different from the Ricci form, sort of like
right.
Ricci form.
It is not actually, it's not
it's the same thing. But
because
on compact manifolds, it's just about the same. Well, I guess like on compact manifolds, you would expect this like Lie derivative terms coming from the Lie form to at least be sort of exact. It's equivalent to some sort of soliton equation. But yeah, I guess I don't know if any of those could conceivably be Hermitian, but they do have these examples now in all dimensions, coming from some homogeneous space constructions. It's conceivable that some of those are secretly complex manifolds and also Bismuth-Ricci flat, because maybe the Lie form is like a killing vector in those, you know what I mean? And then the PDEs would be exactly the same. Like the Lie form would drop out. Maybe. I'm just saying it's possible.
Maybe. So it is worth having a look at that. What is the reference?
I think the title is something like Infinite Family.
Yeah, it's Infinite Families of Bismuth-Ricci flat manifolds, homogeneous Bismuth-Ricci flat manifolds.
Okay, thank you very much. So I'll take a look.
Yeah, the point is that, of course, we do not know whether you have any reasonable invariant complex structures on those spaces for the moment. So in fact, as Jeffrey was saying, the condition you're interested in is something like a soliton condition, a generalized Ricci soliton condition. And in the compact case, probably if you ask also homogeneous, you don't have examples apart from Bismuth-Ricci plot in the Riemannian sense, if you want.
But I still think it's possible that maybe your examples are complex manifolds where the associated Lie form is like a killing, or like the Lie vector is like a killing field. And so then the PDE would be the same. But yeah, anyways,
I see.
I think it's still possible, maybe, but it's something to be checked.
Something that you have to check a posteriori. So there is no complex setting in that.
Yeah, right. Their work, there's no complex structure involved at all. So I mean, yeah, first you have to find which of those examples even has complex structures. So yeah.
Which are the geometries?
Maybe.
Well, you start with a product of two compact semi-simple groups, and then you quotient by an isotropy that is diagonally embedded into it. And of course, you have plenty of examples, and lots of them are even dimensional, so there might be some space probably to find solutions.
Okay, I don't know. Anything else? Any other questions? Okay, well, yeah, thanks again, Ro. It's very nice.
Thank you to you for the invitation.